Hello everyone. So today we are going to do question palindrome partitioning. So basically this question is again of recursion and backtracking. In this question what we are given with a string and we are required to simply return all the valid palindromes which could be possible after partitioning in this particular string. Means here it is given a string S partition is such that every substring of partition is a palindrome. Alright. Return all the possible palindrome partitioning of S. So in this particular, how many types we could partition this string so that it is still a valid palindrome. So here all these are palindromes, right? So one possible partition would be like this one, right? And another form in which it is still a palindrome is means here it was by taking 1 1. Now we can start with directly 2. Now when we do this, then it is a valid palindrome, but when we do this, it is not a valid palindrome, right? But still, if we do only this, then it is a valid palindrome, right? So again, it could be simply like this. But if we take 3, means all 3, then it is not a valid palindrome. So that's why these two are our answer which is being given here. So like this, we are required to make all the partitions which are palindrome. Means basically what we would be doing will simply changing the size of our substring and we'll check that is that particular partition now a palindrome or not. See here when we were doing single means 1 1 partition, then we were checking that yes this particular partition is a palindrome. But here when we were doing by 2 2, then we were checking that is it a palindrome? Yes. Then we were checking for this in 2 length. It is a palindrome? No. So that's why then we were required to check for other portion which was being left, that is this one. And we checked yes it is a palindrome. So we simply put that into our string. So this is what we are required to do in this particular question. So the intuition which comes to mind for doing this particular question is that here we are required to check for all the possible combinations which could be made, right? Means whenever we are checking for 1 1, then we are also required to check for 2 length, then we are also required to check for 3 length. And in all this, one thing is common that we could get back to our previous partition and then we can simply check that is this particular partition now possible a palindrome or not. And moreover here the constraints are simply till the 16, so that's why here recursive solution would work completely fine. So that's why this particular question could be done by using recursion and backtracking. So before this particular coding part, let me walk you through that how we would be writing this particular recursive code. So first thing, before doing any recursive code, what we are required to do is we need to keep 3 things in mind. First is base case, then the options which are there, and the recurrence relation. So the base case is that when our index, because of which we would be traversing our whole array, when that index becomes equals to the size of our input array, then we'll simply push to the answer. That is the base case which will be there. And options are simply the whole input array. That is that particular A, we were having these 3 options. Either we could select single, we could select double, single, or double, or even all 3. So we are having options in such manner that we could select out of these 3. So that's why we are having this whole input array as the option. Now comes the next part about the recurrence relation. For the recurrence relation part, we are simply required to check for what would be the next combination which could be made. That is the partition which could be there for checking that is it a palindrome or not. So that's why a recurrence relation, that would be simply by incrementing the size, of that particular subset by simply incrementing the index of the loop. So now for this part, I, before going to the code, let me explain you that how we will be coding through this recursion tree. Now for this recursion tree part, I have taken this AAB as the example. So we are given with this particular AAB as our input, right? Our index is 0, 1 and 2, and we would be having 3 branches because of the fact that we are having 3 options, that is this first A, then second A, and then third B, right? So now the part is, as in the question it is mentioned that we are required to return valid palindromic partitions, right? So for that fact, first we would be required to check that is present partition a palindrome or not. If that particular partition is a palindrome, then only we will push that to the answer, and after that we will check for further index. Either we can check it by simply getting the substring, that is AAB, or we can simply check it by getting single char of that particular string. So this is how this particular tree is formed. Now in this first branch, we are checking for all those chars which are of 1 length. In this particular, we are checking from all those chars which are of 2 length to 1 length, and here we are checking for all those chars which are of 3 length. Now for this first branch, we are having this I is equal to 0 and index is also equals to 0, right? So here the length of the substring will be simply 1, because 0 minus 0 plus 1, that is the form of the substring which we will be taking. So that's why we are having this A, and we'll simply get more into depth of this through our recurrence relation, means that recursive function which is there. And because of that, what we would be doing now, our I will simply increment and it will become I equals to I plus 1. That is, now our index would also be incremented and our I would be simply equals to I plus 1, and both of them are 1, right? So that's the reason now we will be checking for our second A. So when we check for our second A, so yes, it is also palindrome, so that's why it is also pushed. Now for the next, because of the function, it's I equals to 2, so it will check for the last option which we are having, that is B, and it is also valid palindrome, so that's why this will be again pushed. And then again I will be incremented, but this time because of the for loop, it can't go further, so it simply reaches the base case, and thus it will be simply pushed to our final answer. And then it simply backtracks. Yes, it will simply backtrack, and when it will backtrack, it will simply pop this particular B, and it will reach to this particular AA state. And then further, it, due to that recursive function, it will again go ahead deeper, but now as I has now become equals to 3, so because of for loop, it will simply terminate here, and then it will again return to its parent caller, and then this parent caller has now no further calls, so that's why now this will return to its parent caller, and it will check for further calls in that particular further indices in that particular loop, that is I value. So it will check that yes, it has I values to be checked, so it will check it I equals to 2. Then when it check for I equals to 2, then it sees that yeah, index equals to 1, I equals to 2, so that simply means that it will check for A and B. Here A and B would be checked, but it is not a palindrome, so that's why now this branch won't move further, and it will simply backtrack. And then after backtracking, it will simply check that are there further calls left. Yes, there is one call left which was for I equals to 3, but because of for loop, it won't move ahead, and then this particular will simply backtrack again. And then it backtracks to the final caller, that is the parenmost caller. Then it will check, because of the for loop, it will check for further branches. Now it will go to this I equals to 1 branch, and when it goes to this I equals to 1 branch, then it will check that now my index equals to 0 and I equals to 1, right? So that's why we can check for this 0 and 1, that is this particular subset. So it will check for this AA and it is a palindrome. Yes, so it will push to the answer. Means the temporary answer vector which would be there, it will push to that, not to the final answer. Then it will move ahead and check for I equals to 2. And here it checks that AB, this is not a palindrome, so it won't be able to move ahead with that particular if condition. But it will simply move ahead with this index equals to 0 only. And then it will check for further parts where I equals to 2. And because of that only, when I equals to 2 and index would be simply incremented to 2 only, here it was not able to push into this particular because of the fact that AB was not a palindrome, but it simply moved ahead because index was still incremented, but the recursive function call was not able to be made because of the fact that if condition was not satisfied. So that's why only the I was incremented and now I is equal to 2 and index was again equals to 2. So because of this fact, I equals to index equal to 2 plus 1 would be done, and then the substring would be simply for this particular, and it is a palindrome. So both of this would be pushed to our main answer. And then it will take for further branches, but that won't satisfy because then I equals to 3 would be there. And then it moves to its parent call. Here also I equals to 3, but it won't satisfy the for loop, and thus it will go to its main parent caller. And then it will check for I equals to 2. Here index equals to 0, I equals to 2. So it will check for the whole substring, that is AAB, but is not a palindrome. So that's why it won't move ahead. And by this, it will move further to its parent caller again. And now parent caller has no further calls. So the loop will terminate here. And recursive call would also terminate here, and the final answer would be returned, and our final answer is simply this one. Means this would be added to final answer and this one would be added to the final answer. So now comes the part for coding this particular solution. Means after viewing this recursive tree, we can simply check that yes, there is possibility of checking each and every possibility through the recursive tree. So let us code this particular solution. So let me quickly walk you through the code that how we can do that. Now, how I've coded this particular question is simply like this. Okay, let me first out this particular. Okay, now code is clean. Now comes the part that this particular was given to us by Leetcode only. So here we were given this string s, and here we are having this vector string return, in which I would be simply putting our final answer. And then here we are checking that if s.empty, right? If our parent string is empty, then we are required to return as it is empty answer only. Here I've taken this temporary part array in which we would be storing this particular thing, means these particular. And then I'm simply calling the DFS part. Because we are simply doing DFS in this particular string, that's why I've taken this as there, and now this is the DFS function which would help us to traverse through this whole string in such a manner that we are able to calculate all the possible combinations which could be found and which are palindrome. And this is that palindrome function which will help us to get that is that particular string substring a palindrome or not. Now, in this palindrome function, how we are checking is that I've taken this start and end index, and what we are doing is by using this particular while loop, we are checking that if start and end, if either of them are not equal, then we are straightforward able to return false if we are returning true. So this is what we are doing in this palindrome function. And for this TSS function, what we are doing is, first is the space case. That if our index becomes equals to s dot size, then at that moment only we would be simply pushing our path vector string to our answer. So that is what we are doing here. And in this particular for loop, we are doing the main thing. This for loop is basically our iterative component, which is helping us to traverse through this particular string completely, right? And then before calling the recursive function, we are first checking if that particular position means if A is a palindrome or not, if AA is a palindrome or not, if AB is a palindrome or not. That thing we are checking in this particular if condition. If it is a palindrome, then only it will push to our path vector, and then only it will call for further DFS, and then only it will check for other possibilities by popping out from the path. So this is the thing which we are doing here. Now what we are doing in this path is we are simply getting that particular index, that yes, we are required to start from this index, and the length of this substring is simply determined by the I value which is being there. Why we are doing it like this is that if we are simply at that particular part of the recursive tree, means if we are at this particular part, means if we are at this particular part, then here I value is simply different, right? And index value is simply different, right? So in that particular case, we are simply able to check for different lengths, because here the I value would be simply moving ahead, means it will be simply 2, right? And index would be simply 1 only. And why we are adding 1 to it? Because when both of the index and I value are same, then we are required to have a single length also. So that's why we are adding that one. We simply represent single length characters. And then comes the part of this TFS function. Basically, due to this TFS function only, we are able to move ahead in our recursive tree. Because of this only, our index value is changing side by side, right? And then when we are simply backtracking, then at that moment we would simply pop whatsoever we had filled last time, so that we could explore all other functions, all other parts of the string also. So this was all for the coding part. Now comes the part for time complexity. So for the part of time complexity, here the depth of this particular recursive tree is simply n only, that is size of the input array, because index will go till the size of our input array only, and the width of this particular recursive tree is by choosing the subsequences which are simply 2 raised to power n only. So that's why a time complexity is simply n into 2 raised to power n. That is subsequence size, which is n, because at max the subsequence size could be at n. Because if this AAB, if it would have been AAA, then yes, the subsequence size would have been 3 only, which is exactly the size of this string, and into total subsequences which could be formed. So in that case also, the total subsequences which could have been formed would have been 2 raised to power n only. And the space complexity is simply the size of the recursive stack, that is order of n. So that's why this is a space complexity. So this was all for this particular question. So if you have any doubt, you could click comment out. Yeah, and thank you.